Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on December 22nd, 2025, about 2 days ago. This paper argues that a large language model is not one single policy at all, because every layer and even each attention or feed-forward component implies its own sampleable internal policy, and the authors use that idea to create bottom-up policy optimization, which beats standard reinforcement learning baselines on hard reasoning benchmarks. The paper is titled, Bottom-Up Policy Optimization, Your Language Model Policy Secretly Contains Internal Policies. And as we will see later, the entropy patterns across layers end up directly motivating a surprisingly practical training recipe. Also, the authors shared an accompanying GitHub repo that makes BUPO pretty tangible. You will find the training and run scripts for BUPO and a GRPO baseline, plus the core Virl-based code changes that expose internal hidden states and compute internal layer importance ratios. The repo also includes setup requirements, data and assets, and quick start instructions for Qwen and Llama runs. Figure 1 explains why the authors treat a transformer as many policies, not one. The full diagram lays out 3 ideas: a residual stream pipeline, a way to turn any hidden state into a token distribution, and a staged reasoning pattern. The left panel shows hidden states flowing through self-attention and the feed-forward network inside each layer. The right panel shows unembedding, meaning mapping hidden states back into vocabulary probabilities so they become sampleable policies. The bottom cartoon summarizes Qwen-style progression from exploration to convergence across layers. Figure 2 makes the core point that internal policies start broad and uncertain, then sharpen into a confident choice by the top layers. Entropy is the spread of the token distribution, so high entropy means the model is still exploring many next tokens. The 2 Llama panels show a late, abrupt collapse, where entropy stays high and then drops fast. The Qwen panels, instead, show a smoother, staged decline across layers, which supports more gradual reasoning. Table 1 shows that optimizing from the inside out translates into better reasoning accuracy on real benchmarks. AVG at k means the model gets k tries, and the score is the fraction solved on average, which matters because reasoning outputs can be noisy. In the Qwen 3 blocks, the shaded bottom-up policy optimization row beats GRPO on the overall average. In the Llama Octo Thinker blocks, the same pattern holds, with the biggest jumps showing up on MATH 500. Table 2 shows that bottom-up policy optimization works best when the bottom stage is moderate and when the right internal layer is targeted. The table summarizes ablations, meaning controlled variations of one choice at a time, so the impact is easy to isolate. In the upper block, increasing S-inter, the number of bottom alignment steps, eventually wrecks the scores. In the lower block, fixing S-inter and switching the optimized layer shows that layer choice can further lift the average. Table 4 clarifies why the authors treat internal policies as something you can directly optimize, not just a visualization trick. The full table contrasts LogitLens against the internal policy definition, which matters because the internal policy is explicitly a sampleable token distribution. The definition row shows the key move, where they apply softmax to the hidden state times the unembedding matrix. The trainable row then highlights that this internal policy view supports training, while LogitLens does not. Alright, 2 takeaways stand out. A transformer does not act like one monolithic policy, because each layer and even each module implies its own sampleable token policy, and those internal policies show a clear entropy trajectory from exploration to convergence. The broader implication is that reinforcement learning alignment can target where reasoning is formed, so bottom-up policy optimization can improve hard reasoning with a simple 2-stage recipe. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.